In this video, we're going to discuss how to come up with empirical and molecular formulas for a substance. Firstly, an empirical formula is one that's based on experimental evidence or data and displays the simplest ratio of the numbers of moles of each type of element that are present in a compound. The molecular formula, in contrast, will show us explicitly how many atoms of each type there are in a specific chemical compound. To generate an empirical formula, we need to know something about the relative amounts of each type of element that are present, like these percentages that were given in this problem for mercury, for nitrogen, and for oxygen. While to determine a molecular formula, we'll need additional bits of information like the molar mass or molecular weight of our overall compound. Let's begin by thinking about the empirical formula. To get an empirical formula, we need to have numbers of moles of all of the elements of this chemical compound's makeup. Right now, we know something about the percentages by mass of mercury, of nitrogen, and of oxygen in an ionic compound's formula. These percentages by mass are relative amounts, and as such, if we can assume something about the original compound that we'd analyzed, we can use these percentages in any way we see fit because we can keep a relative measure intact. For example, suppose that we had originally measured a compound that contained 100 total grams worth of mercury, nitrogen, and oxygen. If 76.4% of that 100 grams was due explicitly to mercury, then that would mean that 76.4 grams of our original substance were mercury. One way of dealing with these percents by mass in a problem like this is to simply assume that we've got 100 grams of starting material, and from there, we can replace percentage signs with gram units. By the same token, we'd have 5.34 grams worth of nitrogen in this compound and 18.3 grams worth of oxygen in this compound. From here, we can convert grams into moles. To accomplish this, we'll use the molar mass, or weights of the elements, from the periodic table. The molar mass of mercury is 200.59 grams per mole. The molar mass of nitrogen is 14.01. And the molar mass of oxygen is 16.00. With all of this, we can simply punch numbers into a calculator and come up with corresponding mole quantities of mercury, of nitrogen, and of oxygen. To 3 significant digits, we end up with 0.380 moles of mercury, with 0.381 moles worth of nitrogen, and with 1.14 moles worth of oxygen. From here, in order to compare these mole quantities and make an empirical formula for this compound, we're going to set up a mock chemical formula that includes these mole quantities as subscripts. Remember, a chemical formula can show us the ratio of moles of atoms of every type that make up that compound. Here we've got numbers of moles of every atom that makes up this compound, so why not build a mock chemical formula with them? But unlike all the chemical formulas we've seen up to this point, this mock chemical formula has fractional quantities of atoms. We want our chemical formula, a proper one, to show whole numbers of atoms instead. To accomplish this, while maintaining the same ratio of atoms, mercury to nitrogen to oxygen, we can divide each one of these subscripts through by the smallest quantity among them. And as we do so, we'll convert this into a more palatable chemical formula. 0.380 divided by itself is 1. So we have a subscript of 1 corresponding to mercury. 0.381 divided by 0.380 is for all intents and purposes 1. It's close enough to a whole number that we can round it to that whole number. Any rounding error is associated with our inability to make perfect measurements and our use of significant digits. For oxygen, 1.14 divided by 0.380 gives us 3. At this point, we have converted a chemical formula with fractional subscripts into one with whole number subscripts. The ratio of atoms mercury to nitrogen to oxygen is in the simplest form in this whole numbered subscript formula, and as such, we are done and have arrived at an empirical formula for this compound. That formula based solely on experimental evidence, for which we used the mole ratios of every element that makes up this compound. So again, the steps that we'll take to determine an empirical formula are: first, determine the number of moles of each element that makes up a compound. We've done that here by converting our percents by mass, first into mass, dropping the percent and replacing it with grams, and then converting those masses into moles, using the molar masses we get from the periodic table. From there, we simplify ratios of subscripts for each element down simply by dividing every single one by the smallest number among them to keep the ratio intact and generate whole numbers instead of fractional subscripts. So next, let's think about writing a molecular formula for this compound. To accomplish this, we'll need to think about the precise number of mercury, of nitrogen, and of oxygen atoms that make up the actual chemical substance. To get a handle on how many atoms of each type make up that actual chemical substance, we need to know something about the nature of that actual chemical substance in the first place. In particular, we need to know the molar mass or molecular weight of the actual compound. We're told here that that is 525.2 grams per mole. Does that match the molar mass of the compound whose empirical formula we've already written? Well, in order to determine that, let's determine the formula weight, or FW, for this particular empirical formula. The empirical formula that we've written contains 1 mercury, and mercury has a molar mass of 200.59 grams per mole. It contains 1 nitrogen, 14.01 grams per mole, and it contains 3 oxygens, each one 16 grams per mole. In total, our formula weight for HgNO3 is 262.60 grams per mole. This formula weight is different from the actual molecular weight of the substance that we know from our problem up above. The molecular weight, or MW, for our actual molecule is given as being determined to be 525.2. So we know that our empirical formula does not match our molecular formula. In order to figure out how far off we are, we're going to calculate what I call a scaling factor. The scaling factor represents the ratio of the molecular weight of our actual substance to the formula weight of our empirical formula. This should work out to being very close to a whole number, if not a whole number precisely. For this particular example, our molecular weight for our actual substance is 525.20 grams per mole, and the formula weight of our empirical formula, or 262.60 grams per mole. Units cancel out, we end up with just a number. The number here in this case is indeed precisely a whole number. It is 2. The scaling factor tells us that we are 2 times less massive in our empirical formula as we should be in our molecular formula, our actual chemical compound. Therefore, with this scaling factor, I'm going to multiply every single subscript in our empirical formula by that number to get our molecular formula. There is 1 mercury in our empirical formula. I'm going to multiply that by 2 and have 2 mercuries instead. There's 1 nitrogen in our empirical formula. I'll multiply that by 2 to have 2 nitrogens instead. There are 3 oxygens in our empirical formula. I'll multiply that by 2 to get 6 instead. The actual molecule that we've analyzed has 2 mercuries for every 2 nitrogens for every 6 oxygens. Perhaps another way to write this, if we recognize that by virtue of this being an ionic compound and NO3 being recognizable as a polyatomic anion, we could have shown the equivalent formula as Hg2 NO3 2, or mercury 1 nitrate. Either of these are acceptable. Both of these are representative of the same molecular formula for the molecule that we've analyzed. Again, our molecular formula differs in mass from our empirical formula. In that case, we came up with a scaling factor by which we could multiply every subscript in our empirical formula to identify our molecular